Hey everyone, and welcome back to another video. In this video we're going to be going over Counting and Probability Unit 2. This is the second video of the counting and probability topic. In the first video we went over counting in the form of combinatorics, and in this video we're going to be going over probability, which is the second half of this topic. So in the first half of this video, in the first third of this video, I should say, we're going to be going over the language of events and sets, which realistically is the language of probability. When we're referring to the probability of an event, how do we represent that? That's what we'll be going over. In the next section of this video, we'll be going over the fundamentals of probability. That is, what is a probability bounded by between 0 and 1, 0 and 100%? How do we represent a complement? What does a complement represent? And how do we calculate that? Then we're going to go into more complex probability calculations like conditional probability, the probability of an event happening given that another event has occurred, and seeing how that feeds into another concept called independence. And we'll be looking at tests for independence, looking at dependent and independent events, and a lot more. So I'll get straight into it and I'll turn off my camera.
So before I go into any definition of probability, what I'm going to be looking at is the language of outcomes, sample spaces, and events. The language of events and sets, that is. To illustrate the concept of a sample space, let's consider a six-sided dice. The sample space of all the possible outcomes we can have from rolling a six-sided dice are rolling a 1, 2, 3, 4, 5, or 6. Each of these distinct elements, we will refer to them as elements, represents the possible outcomes of rolling a six-sided dice. What an event is a collection of outcomes. For example, we can refer to an event A as the event that we roll either a 1 or a 4, or B as the event that we roll an even number. Okay? So now we've come to a definition of outcomes, sample spaces, and events. Let's introduce some more set language and notation. This first point we talk about the complement of an event. So if A, to illustrate, if A is equal to the event that we roll a 1 or a 4, then the complement of A is equal to the event that we roll a 2, a 3, a 5, or a 6. In other words, the complete opposite of A. The complement of A is precisely this. It is the negation of the event A. If A is the event that we roll a 1 or a 4, then A complement is the event that we do not roll a 1 or a 4. We can also refer to complements in this way or in this way. So that's complements. Now let's take a look at intersections and unions. If I talk about the intersection of A and B, this is equal to the number 4. And this is my intersection. Why is it equal to the number 4, you may ask? Well, I'm about to tell you. So, when we talk about this symbol, we refer to the symbol as AND, or the intersection of A and B. So, at the intersection of A and B, both event A and event B have to be satisfied. The only way that both event A and B are satisfied is if we roll a 4. In the case that we roll a 4, we have rolled a 1 or a 4, and we have rolled an even number. Let's take a look at the union of A and B. When we talk about this symbol, we say OR, and this is referred to as the union of A and B. The union of A and B is equal to 1, 2, 4, 6. In this case, only one of A and B needs to be satisfied for the entire relation to be satisfied. Here, only A is satisfied. Here, only B is satisfied. And here, only B is also satisfied. but the fact that one of A and B is satisfied is enough to satisfy both. If we represent this as a Venn diagram, and we have our events A and B, then event A includes 1 and 4, and event B includes 4, 2 and 6, and everything outside is 3, 5. Then our intersection of A and B represents this part here, which satisfies both A and B, whereas our union of A and B represents everything here. This is our union of A and B, and the red is our intersection of A and B. Alright, cool. So we've ticked off our intersections and unions then. And now let's take a look at 3 sets. If we have our 3 sets A, B, and C, then the intersection of A, B, and C is this bit here, where all A, B, and C are satisfied. If we're looking at the union of A, B, and C, then that's equal to everything here. Alright. The concept of the intersection is also really central to understanding what mutually exclusive events are. So let's take a look at mutually exclusive events then. So, mutually exclusive events. Mutually exclusive events refer to events that cannot occur at the same time. For example, the event that we roll an odd number cannot occur at the same time as us rolling an even number. So the event of rolling an odd number is a mutually exclusive event to rolling an even number. So, if we were to represent this in Venn diagram form, and we have a look at this, and we look at A, and let's say C is the event that we roll an even number, so we roll a 2, 4, or a 6, and D is the event we roll an odd number, we can see that C and D share no intersection. This is the characteristic of two mutually exclusive sets. C and D, the number contained within C and D, is equal to 0, and the event C and D is the null set. If we were to represent this more properly on a Venn diagram, we would represent this in this way. This is what the Venn diagram of mutually exclusive events looks like. Okay, so we've gone over the language of events and sets, and examples for you to do. I recommend having a look at Sadler. Now, let's take a look at the fundamentals of probability. What probability is most fundamentally is it is a measure of the likelihood of an event occurring. So, importantly, a likelihood of an event can be between 0 and 1. 1 refers to the event as being certain to occur, whereas 0 refers to the event as being impossible. Anything in between is something in between impossible and certain. The probability of any event is therefore said to be bounded by 0 and 1. Because we've defined a probability as bounded by 0 and 1, we can come to a mathematical definition of what a complement is. If A, again, is the event that we roll a 1 or a 4 on a 6-sided dice, alright, and A bar is the probability that we roll a 2, a 3, a 5, or a 6, we can say that the probability of the complement of A is equal to 1 minus the probability of A. Sorry, that should be an A. So let's say we have our six-sided dice and it is a perfectly fair six-sided dice. Then the probability that we roll a 1 or a 4 is equal to 2/6. Probability of A equals 2/6. Therefore, the probability of A bar is equal to 1 minus 2/6, or 4/6. If we look at the event A bar, we can verify this. Here we have 4 different events. Each of these has a probability of 1/6 associated with it. Therefore, the probability of A bar, given this, can be calculated to be 1/6 plus 1/6 plus 1/6 plus 1/6 is equal to 4/6, just as expected. Okay, so we've had a look at the likelihood of the occurrence of an event. We have defined 0 as impossibility and 1 as certainty, and we have had a look at the mathematical definition of a complement. Now let's take a look at how we get this mathematical relationship. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. Let's take a look at a Venn diagram. And let's take a look at the right hand side. We have an event A and we have an event B. This is in a different event A to the event A we're talking about here. This is a more general event I'm referring to. So, the probability of A refers to this part here. The probability of B refers to this part here. So then, the probability of A intersect B refers to this part here. If we add the probability of A and the probability of B, then we count the probability of A intersection B twice. As a result, we need to subtract away one probability of A intersection B to get to our probability of A union B. And so this formula and this equation holds. Okay. So, relative frequencies. Let's give an example of this dot point and then we'll move on to conditional probability and independence. So, let's say we have a frequency table. Let's say we're looking at marks distribution. Okay. Let's say we have students, a set of 20 students taking a test, and we generate a frequency table, and we look at the grades. We see C, B, and A, and we have a frequency of students within each of these ranges, and we have 6, 7, 3, and 4. Okay, and let's say we are trying to calculate the probability that we select someone who got an A grade. The probability of selecting someone who got an A grade will be equal to the number of people who got an A grade divided by the total students who took the test, which I represent by a U to represent the universal set. The universal set here being the 20 students that took the test. The number of students who got an A is 4, and the number of students who took the test is 20. Therefore, my probability of selecting a student who got an A grade is 4 divided by 20, or 0.2. Alright, let's move to conditional probability. Conditional probability refers to an event A given that an event B has occurred. The probability of event A, like this, refers to the probability of event A occurring given that B has occurred. For example, the probability that I go to a swimming pool given that it's sunny outside. Alright. If we want to represent the conditional probability relationship in a Venn diagram, we would do it in this way. Since this represents a given B, this implies that B has already occurred. So we consider our sort of sample space here as B, this part here. Then if we're looking at a given B, that will be this section here. This is the event A occurring within B having occurred. So my probability of event A occurring given that B has occurred is equal to the intersection of A and B divided by the probability of B. Alternatively, I can also write this as the number of people in A and B divided by the number of people in B, or the number of elements in A and B and the number of elements in B. Now that we've come to a definition of what conditional probability is, we can take a look at independence. What independent events refer to are events that do not have any influences on each other in terms of probability. For example, let's say the probability that it rains in California and the probability that I go to the pool in Perth. These two are considered independent events. Mathematically, we can write that as probability of A given B equal to the probability of A. That is, the probability of an event A occurring given that an event B has occurred is the same as the probability of the event A occurring by itself. This indicates that A and B are independent events. If we recall that the mathematical definition of a conditional probability is the probability of A intersect B divided by probability of B, we can rewrite this equation as probability of A intersect B divided by probability of B equal to probability of A. Rearranging, we get P A intersect B equals probability of A times probability of B. So, if two events are independent, then the probability of A intersect B is equal to the probability of A multiplied by the probability of B. This is referred to as our test for independence. Okay. So we have understood the notion of conditional probability, we've used the notation, we have understood the notion of independence, we have established this formula, and let's have a go at applying this. So let's say we have a probability of A intersection B of 0.06, we have a probability of A as 0.2, and a probability of B as 0.3. If we want to test for independence, we need to show that this equation is satisfied. Probability of A intersect B is equal to 0.06. Probability of A times the probability of B is equal to 0.2 times 0.3, which is 0.06, which is the same as the probability of A intersection B. Therefore, A and B are independent. Okay. Some more examples are given in your Sadler textbook, and you can have a look at Nelson and O.T. Lee as well. Alright, let's take a look at some more representations of probabilities that particularly make a lot of use of conditional probability. So, what way of representing events occurring that uses conditional probability is tree diagrams, for example. So, if we have a look at, for example, the event that I walk to school, or let's say the event that I take the bus to school, A is the event I take the bus to school, and B is the event that it rains. And these, you can probably guess that these are probably dependent events. That is, the probability that it rains affects the probability that I take the bus. Or the event that it rains affects the probability that I take the bus. When we're looking at tree diagrams, we represent them in this way. What this probability represents is the probability of A occurring. This represents the probability of A bar occurring. Here's where conditional probability kicks into play. This bit here represents where B occurs given that A has already occurred. And this represents B complement given that A has occurred. This represents B given A complement has occurred, and this represents the probability of B complement given A complement has occurred. Recalling that the probability of B given A is equal to the probability of B intersect A over the probability of A, we know that the probability of A and that the probability of B given not A is therefore equal to probability of B intersection A dash over probability of A dash. We can rearrange these equations in this way. This one can become probability of B given A times the probability of A being equal to the probability of B intersection A, and this becomes the probability of B given not A times the probability of not A being equal to probability of B intersection A dash. Let's take a look at what these two represent in a Venn diagram. So I'll put this one in red. B intersect A. B intersect A represents this section here. What about B intersection not A? That is everything outside of A and within B. So here. So summing this blue section, which I let as this, with my red section, I get the probability of B occurring. And so I can write my probability of B, derive my probability of B from a tree diagram by summing the multiplication of these arms. That is equal to my probability of B. More examples are given in Sadler, Nelson, and O.T. Lee, so you can have a look at that. But other than that, that is everything for probability. I have gone over it quite quickly, so if you have any questions, please do let me know.